I am going to build a Tesla coil to launch electromagnetic waves and then construct a simple loop antenna to detect them. The experiment I will be doing will be very similar to the one that Heinrich Hertz did when he proved the existence of electromagnetic waves. Here is the diagram of our Tesla coil. It is composed of 5 components. We have a transformer. I will wind the primary with 4 turns counterclockwise, and it's around the secondary, which will be wound clockwise with 1065 turns. I have a power transistor here, which will act as a switch, a resistor, a diode, and I will use a light-emitting diode, and a DC power supply. Many Tesla coils will have a circuit that incorporates a spark gap as the switch instead of a transistor, as Tesla originally did. At the end of this video, I'll explain how this circuit results in a high voltage, high frequency signal coming off of the secondary. I'm going to wind the secondary around this 3/4 inch piece of PVC tube, and I'm going to drill small holes at each end through which I can feed the wire. I'm going to wind the secondary by hand around this PVC tube, repurposing some magnet wire from this coil. Obviously, I did not wind this coil by hand. I'm at 200 turns, and I've put electrical tape around the end of the coil. I'm at 300 turns. Here is the finished secondary coil, and it consists of 1065 turns. I wound the primary around this larger diameter PVC tube, and I used bare copper wire, so by where I connect to it, I can adjust the number of turns in the primary. Looking down from the top, the primary coil is wound counterclockwise and the secondary coil is wound clockwise. I've glued the secondary down, and my primary will fit right over it. And I've wired up the circuit consisting of the power switching transistor, the diode, the resistor, and where I will connect the DC power supply. I'll now connect the circuit to the primary. And now I just need to add my DC power source. I've attached a 9-volt battery, and I know my circuit is oscillating because the light-emitting diode is coming on and off, but the electric field intensity is not strong enough to cause ionization at the end of this secondary. A way to test that there's an electric field around the secondary is with a fluorescent tube. If I bring the fluorescent tube close, you see that it starts to light up. Move it away, it goes off. When you put a fluorescent tube in a fixture, there's a voltage between the two ends, an AC voltage that causes an AC electric field intensity inside the tube. The AC electric field that's emanating from the Tesla coil is going through the tube, and that is what's causing it to light. This is the experimental setup that Heinrich Hertz used to verify the existence of electromagnetic waves. He had a circuit that would build up the voltage across this gap until the electric field intensity inside that gap got to the dielectric breakdown strength of air, and he would get a spark. So this gap would go from an open circuit to a short circuit. This would launch an electromagnetic wave. Hertz's detector or receiving antenna was a loop of wire with a small gap. So as the electromagnetic wave went through his loop, an electric field intensity would build up in the gap. If that intensity was large enough to cause dielectric breakdown, he would see a spark indicating that he had received an electromagnetic wave. I'm going to do an experiment fairly similar. I'm going to use the Tesla coil we've been looking at to generate our electromagnetic wave, and I'm going to use a loop to detect it, but instead of having an open circuit and looking for a spark, I'm going to attach an oscilloscope at that point to look at the wave that antenna is receiving. I've taken a piece of magnet wire and formed a loop, and I've removed the insulation off the ends, and I will plug these ends into my oscilloscope. I have an Analog Discovery 2, and one of the pieces of test equipment in it is an oscilloscope, and it connects directly to my laptop, and I'm going to plug in my loop antenna into the oscilloscope inputs. I have the Tesla coil off, and as I move the loop antenna around, you see that the display on the oscilloscope is flat. I will now plug in the 9-volt battery to turn the Tesla coil on. With the Tesla coil on, the loop antenna is picking up an AC signal. And as I move the loop antenna closer to the coil, the amplitude is increasing. The period is about 0.6 microseconds, which is a frequency of 1.67 megahertz. So I'm generating an electromagnetic wave with the Tesla coil and detecting it with the loop antenna. I have the loop antenna attached to the wall and the output from the loop antenna displayed on the screen. The Tesla coil is currently off, so let me turn it on. And we see the AC signal that the loop antenna is picking up. Turn the Tesla coil off, the signal goes away. On, off, on, off. I am now going to connect two 9-volt batteries in series so that I can run the Tesla coil with 18 volts. The electric field intensity at the tip of the secondary is now large enough to ionize the air. I will now put 3 9-volt batteries in series so I can run the Tesla coil with 27 volts. Let's look at how this circuit operates. At t equals 0, we will close this switch, and there will be a current flowing into the base of the transistor, turning this transistor on. That will result in a current flowing through the primary. The resulting magnetic flux in the primary will be coupled into the secondary. Let's focus on the operation of our coupled coils. I will define I sub P as the current flowing into the primary and I sub S as the current flowing out of the secondary. To make it easier to visualize, let me separate the primary from the secondary. Although it's not a perfectly coupled transformer, I'm going to assume all the magnetic flux from the primary flows through the secondary, and I'm going to define the direction of the magnetic flux in the primary, phi sub p, as pointing upwards, and that in the secondary, phi sub s, as pointing downwards. So phi sub p is equal to minus phi sub s. Looking down from the top, the primary is wound counterclockwise and the secondary is wound clockwise. Let's apply Faraday's law to our primary. In applying Faraday's law, you put the fingers of your right hand in the direction of the integral of E dot dl, and then your right thumb points in the direction of the magnetic flux. Integrating around our circuit, we're going to go counterclockwise. So if you put the fingers of your right hand in the direction of the integration around the primary, your right thumb points in the direction of phi sub p. Assuming negligible resistance in the windings of the primary, the integral of E dot dl around our circuit will just give us minus V sub p, the input voltage to the primary. Now we will apply Faraday's law to the secondary. We are going to integrate around our circuit going clockwise around the secondary. So if you put the fingers of your right hand in the direction of our integration around our secondary, your right thumb points in the direction of phi sub s. Again, because of negligible resistance in the windings of the secondary, the integral of E dot dl around our circuit will just give us minus V sub s. Since phi sub p is equal to minus phi sub s, minus the voltage across our secondary will equal the number of turns of the secondary times the change in magnetic flux in the primary with respect to time. From our result for applying Faraday's law to the primary, let's solve for d phi sub p dt and substitute for d phi sub p dt into our application of Faraday's law to the secondary. The voltage across the secondary will be the negative of the voltage across the primary and increased in magnitude by the ratio of the number of turns in the secondary to the number of turns in the primary. With our assumption of a perfectly coupled transformer, the input power to the primary, V sub p times I sub p, is equal to the power coming out of the secondary, I sub s times V sub s. So we can then get this relationship between the current in the secondary and the current in the primary. Even though the top of our secondary is not connected to anything, a current can flow in the secondary. Charge will accumulate at the open end of our secondary coil. There will be a capacitance associated with the end of the secondary. You can think of one conductor of that capacitor as the end of the secondary, and the other end wherever the electric field lines that are emanating from the charge on the end of the secondary are terminating. That will be some nearby conducting object, and so the capacitance is going to be small. To further understand the operation of this circuit, I ran a simulation. To account for the capacitance associated with the top end of the secondary, I used a 0.2 picofarad capacitor. I applied the 9-volt battery at t equals 0 seconds. This supplied a base current, turning our NPN transistor on and causing a current to flow through our primary, and we can see that initial current in our primary as this spike right here in our simulation. the current flowing out of our secondary is actually negative, so it's actually flowing down through this secondary, resulting in a negative charge on the top plate of our capacitor. And in our simulation, we can see that that initial negative secondary current results in a negative voltage across the capacitor. With this capacitor charged up, the current through the secondary will fall to zero, and if you look at this loop right here, you'll see that the voltage to the base of the transistor becomes negative, shutting off this transistor. You essentially have an LC circuit here, so now current is going to flow up through the diode around this loop, so the charge will transfer, the positive charge from the bottom plate of the capacitor through the diode to the top plate of the capacitor. You can see that happening here with the voltage across the capacitor going from almost minus 300 volts up to plus 300 volts as the charge is transferred. This raises the voltage at this point to the base of the transistor, turning the transistor on and causing another primary current to flow. Here is the voltage across that diode and the current flowing through that diode. And we can see that the result is that we get an oscillation with a period of about 1.2 microseconds. The period of the circuit we actually built was 0.6 of a microsecond, and the difference from the simulation is because I did not know the exact values to use for the capacitance of the open end of the secondary or the inductances of the primary and secondary coils.